Okay, so welcome back. Here's what we were talking about last time, which was null space of a matrix. So the null space of a matrix was defined to be the set of all solutions to this homogeneous equation ax equals 0. Um, and so one of the things about the null space that is kind of a nice fact is if you're given a vector and asked whether or not it's in the null space, it's really, really easy to check. So checking that a vector is in the null space is easy. You just multiply that vector by a and see if that's a zero vector. So if it is a zero vector, then that vector is in the null space. If it's not, then that vector is not in the null space. But describing the null space of A, that is, when I say explicitly describe, ideally I mean describe a spanning set for the null space. What did that mean? So what we had to do in order to do that was we set up the equation ax equals 0, set up the augmented matrix A, last column is 0, do as many row operations as we need to get it into a form where I can solve this thing in parametric vector form. Writing out a general solution, this is what I obtained. And so in that particular example, for instance, we were able to say that the null space for that matrix A was the span of these three vectors that I found. Okay. This is one of the most important uses of that parametric vector form that we did way back in chapter 1, is so that we can actually explicitly find a spanning set that describes the null space. So the null space is the span of those three vectors. That means that any vector in the null space is a linear combination of those three vectors, u, v, and w, that I found. Okay, so there's a couple of things to say here. One, and I make this, I bring this up knowing that I'm going to talk about it a lot more in the future anyway, but it's nice to notice. So let's say that I had asked you a different question. So looking at this example that we did last time, let's say you had seen similarly worked things, and you knew that by this process, you could find a spanning set of some number of vectors that spanned the null space. Okay, so let's say that you knew this process always worked. You'd seen a bunch of examples like this. So then going back here, what if at this point I stopped and I asked you, how many vectors is it going to be? How many vectors are going to be in this spanning set? Now, that question, it turns out, is not that well posed, because a spanning set could have a lot of garbage in it. I could toss in an extra 10 vectors in that set. You know, that spanning set would still span A. So if I had the null space of A, sorry. So if I had the vectors u, v, and w as I labeled before, and then I threw in just like 10 random vectors there, then the same, it would at least span the null space. And I could throw in the vectors in such a way that it didn't add anything. Basically, it didn't add anything extra, because I could throw in vectors that were just linear combinations of u, v, and w, right? So this question, I understand, is not well posed, but let's say that we're being smart here, and I'm saying, let me ask you, like, what's like the most efficient number of vectors that will get the job done? Could you answer it from looking at this? Well, I mean, maybe. What is the tie-in with 3? Why did I get 3 vectors? Where did those 3 vectors arise? Those 3 vectors arose as the vectors multiplying x of 2, x of 4, and x of 5. What are those variables for this equation? Oh, they're the free variables. Oh. So then if I looked at this, and I noticed that there are 3 free variables, x of 2, x of 4, and x of 5, those free variables, we know, like the existence of a free variable for an equation like ax equals 0, tells us something, right? It tells us that there exist non-trivial solutions to this. But then the number of free variables basically tells me how many free choices I have here. And this is going to tell me how many of these vectors I should expect, like this. Now, if you didn't quite get that argumentation, it's okay, because we're going to be doing that over and over and over again. The main thing to get from this is the null space is easy to check if something is a member of the null space, but actually explicitly describing all the vectors in the null space, it takes a little bit of work. It's not hard. It's literally the exact same amount of work as it takes to solve ax equals 0 generally. But solving ax equals 0 generally is, we'll call that, some amount of work. And so it takes some amount of work to explicitly describe the null space. Okay, so now I want to talk about kind of a dual object here called the column space. So here's a definition. The column space. So the column space of an m by n matrix A, okay, written as the column space of A, so call A, is the set of all linear combinations of the columns of A. So if A is the matrix that has columns A1 through AN, because it has n columns, then the column space of A is just the span of that set of vectors that make up the columns of A. Okay. Well, since the span of a list of vectors was seen to be a subspace previously, then we have the following theorem, which immediately follows from that fact, that the column space of a matrix A, that's an m by n matrix, is a subspace of R. Where do these columns live? Right, so there are n of them, but they have m entries. So this is a subspace of Rm. Okay. So the column space is a subspace of Rm. The proof is that we already saw that the span of a list of vectors is a subspace of R, or is a subspace of the ambient space that it sits inside. So the span of a bunch of vectors in Rm is itself a subspace of Rm. Okay. So then note the definition itself gives us an explicit description of the column space. So before, right, so I had asked, give me an explicit description of the null space of a matrix. And when I asked that, we had to do some work to figure out that, the null space of A was the span of some vectors that we found, right? But the definition of the column space gives it automatically as a span of an easy list of vectors. It's just the columns of A. So to come up with an explicit description of the column space is trivial because it's just given to you in the definition. Okay, so if you have the matrix A, writing out exactly what the column space is trivial. Okay, note also that there's another way of writing the column space. Okay, so since the column space is a linear, or is the span of A1 through AN, the columns of A, remember the span is the set of all possible linear combinations of whatever list of vectors you have here. So column space is the set of all linear combinations of the columns of A. So another way of saying that is that the column space of A is the set of vectors B in Rm such that AX is equal to B for some X in Rn. Check with yourself that that makes sense. Why does this make sense? Well, a vector is in the column space if it can be written as a linear combination of the columns of A. But if it can be written as a linear combination of the columns of A, we'll say the weights in that linear combination are x sub 1 through x sub n, then there's a solution. AX equals, there is a solution to the equation AX equals B, where this vector x is the weights, or they're the weights, right? This vector contains the entries that are the weights in that linear combination. Okay. So here's another way of thinking about the column space. Okay. So then what does this mean? Well, this means that note. So 3 notes in a row here. What do I have to do to check if a given vector is in the column space of a matrix A? So what do I have to do to check if a given vector is in the column space of A? Well, the answer is I need to solve AX equals B if possible, i.e. I need to know if AX equals B is consistent. Which is not hard, but it requires work, right? We've defined the solving of an equation AX equals B, or finding whether or not an equation AX equals B is consistent, requires some work, and so checking whether or not a given vector is in the column space requires some work. This is contrasted with the null space, of course, because as we saw, checking whether or not a vector was in the null space was very easy. So one more fact here before I go through explicitly the contrast between these things. So the column space of an m by n matrix A is all of Rm if and only if the equation AX equals B has a solution for each B in Rm. Oh, I'm totally off the page. There we go. All right. So the column space of an n by n matrix is all of Rm if and only if the equation AX equals B has a solution for each B in Rm. So let's think for a second. If the column space of a matrix A is all of Rm, what that means is that every vector in Rm is a linear combination of the columns of A. But if any given vector B is a linear combination of the columns of A, that means AX equals B has at least one solution for every B. All right, so this fact basically requires no proof. It's basically true by definition of these things. Okay, and so before I move on here, and we are going to I'm going to ask plenty of questions about this stuff, and we are going to do many examples of this stuff. I think it is easier to go through the list like this so that I don't actually have to write it out. Yeah, so someone said a transformation of A would be onto in that case. Yes, so we're about to see how this relates to linear transformations. So this page is in your textbook. In my version, it's on page 206. So in whatever edition you're using, this table will exist somewhere. So here's what the table says. So this is the contrast between the null space of A and the column space of A for an n by n matrix A. Okay, so going down the null space A. Null A is a subspace of Rn, whereas col A is a subspace of Rm. Okay, null A is implicitly defined, that is, you're given only a condition, that is Ax equals 0, that vectors in null A must satisfy. But col A is explicitly defined, that is, you're told exactly how to build vectors in col A. So this is the statement, basically, that null A, being implicitly defined, part 3, says it takes time to find vectors in null A. Row operations on the augmented matrix A0 are required, but to find vectors in col A is trivial because you're just told that it's linear combinations of columns. So pick any linear combination of columns of A and you've got a vector in col A. So the vectors of the columns of A are displayed, the others are formed from them, right? Okay. So for the null space, there are no obvious relation between null A and the entries in A. But for the column space, there's an obvious relation between column space of A and the entries in A, since each column of A is in the column space. Okay, number 5 here, a typical vector V in null A has the property that AV equals 0. A typical vector V in col A has the property that the equation AX equals V is consistent. Okay, now, moving on, given a specific vector V, it's easy to tell if V is in null A. You just multiply V by the matrix A. But that question for the column space is actually harder because given a specific vector V, it may take time to tell if V is in the column space of A because you have to do row operations on the matrix AV. Okay? So then these last couple of things I'm going to add in even though I'm about to talk to them now, or I'm about to talk about them right now. So here, the null space of a matrix is the 0 subspace if and only if the equation Ax equals 0 has only the trivial solution. So, the wheels are already turning in your head thinking about what that means. If you know that Ax equals 0 has only the trivial solution, then that means, well, if this has only the trivial solution, then its columns are linearly independent, for instance. So 7, for the column space of A is Rm if and only if the equation Ax equals B has a solution for every B in Rm. So it's consistent for every single B in Rn. So that gives us immediately these next things. So the null space of a matrix is the 0 subspace if and only if the linear transformation that sends x to Ax, so A is the standard matrix for that linear transformation, is 1 to 1. And the column space of A is Rm if and only if the linear transformation that sends x to Ax maps Rn onto Rm. Okay, so that was a lot of stuff to go through. We are doing what we do best in this course, which is we come up with a new definition, new notation, new terminology, and then we use that to tie all of the stuff that we've done before, or rather maybe to be able to describe something that we did before in new language. Okay, and there's a reason for this because it makes our life easier depending on the context that we're in. So, technically, I haven't talked about linear transformations between vector spaces. We've talked about linear transformations between Rn and Rm, but not between general vector spaces. So, a linear transformation T from a vector space V to a vector space W is a map that assigns to each vector x in V a unique vector Tx in W such that, firstly, a T of U plus V is TU plus TV for all U and V in V. And secondly, the other condition of linearity, T of CU is C TU for all U in V. And all scalars C. I should say that. There we go. Okay. All right. Okay, so quick definition. The kernel of T is the set of all U in V such that TU is equal to the 0 vector. Okay. That might ring some bells. And the range of T is the set of all vectors in W it's the set of all vectors in W of the form Tx for some x. So how it was defined before for some x in V. Okay. So the kernel is a subspace of V. The range is a subspace of W. Maybe I'll say that. Note. So in fact, the kernel of T is a subspace of V, and the range of T is a subspace of W. Okay. As you might have already guessed, if the kernel of T is the 0 subspace of V, T is 1 to 1. And if the range of T is all of W, then T is onto. So note the kernel of T being the 0 vector. This happens if and only if T is 1 to 1, and the range of T is W if and only if T is onto. Okay. All right. We're going to be using this repeatedly, so you don't have to worry too much if you didn't see that relationship immediately. But this is the idea. In fact, we could have defined these things for our linear transformations between Rn and Rm just as well. Okay. So what does this allow us to do? All right. So note this allows us to study linear transformations that are not matrix transformations. Now, we're not going to be doing that really in this course, but that is one benefit of this generality. All right, so I mentioned this previously when we talked about linear transformations, because I said the linear transformations that we discussed prior between Rn and Rm, those are always matrix transformations. But the more general notion of a linear transformation, that is one between vector spaces, actually we can talk about things that are linear transformations by the definition, but actually um, go between spaces that are not finite dimensional. That is, they don't have an associated matrix. So there is no standard matrix A for those transformations. So I brought in the word dimension there that I won't use again until we actually understand what that means. So for instance, here's an example. Let V be the vector space of all real valued differentiable functions on an interval, say AB. Okay. Okay. All right. Let W be the vector space of all continuous real valued functions on AB. Okay. Let D from V to W be the differentiation operator. Right. Well, then the derivative of a sum of two functions, of course, is the sum of the derivatives. And the derivative of a constant times a function is constant times derivative of function. So D is a linear transformation. Right? So when I ask you, give me an example of a linear transformation that is not a matrix transformation. Here is a canonical example of one of those things. Okay. Now we'll see later that if you're willing to accept a matrix that has infinite entries, well, then it's kind of sort of a matrix transformation, but it's not technically a matrix transformation. Okay. All right. Now, don't worry too much about that because we won't be doing this that much, so we won't be doing much of this. I'm merely bringing this up so that you can be put at ease when it comes to questions of like, why are we moving to general vector spaces rather than keeping everything in Rn and Rm? Okay, this is the reason. The reason is basically through almost no extra work, you get a ton of extra language that allows you to describe situations that are way more general than you were dealing with before. Okay. So that is that. Okay. All right. And so, moving on. The next thing I want to discuss is linear independence in generic vector spaces. So, you might say, what are we doing? We've already talked about all these things. Well, one, we didn't talk about them in exactly the same way, but we're redoing this stuff in our language of generic abstract vector spaces, right? So linear independence and bases. What do these things mean? Well, a lot of these definitions are going to be very, very familiar. It's just rather than having vectors in Rn, you have vectors in a vector space V. Okay, so some definitions. A set of vectors, that is V1 to Vp, in a vector space V is said to be linearly independent if the vector equation C1 V1 up to CP VP equals the zero vector has only the trivial solution. Okay, so you're familiar with this now. Okay. All right, if there exists a non-trivial solution, at least one is all it takes, to, we'll call this equation star. So if there exists a non-trivial solution to star, the vectors are said to be linearly dependent. And that solution is the linear dependence relation. So I'm not going to write that, but that is the same as before. Okay. So just as before, we define a set containing a single vector to be linearly independent if and only if the vector is non-zero. A set of two vectors is linearly dependent if and only if one is a scalar multiple of the other. And then any set containing the zero vector is linearly dependent for that reason. So the following theorem is going to be something that had an analog before. So we actually saw this before, way back in chapter 1. An index set of vectors, say v1 to vp, of two or more vectors with, so we've labeled these in such a way that v1 is not the zero vector, so maybe one of the others is, but v1 is not the zero vector, is linearly dependent if and only if some v sub j with j bigger than 1 is a linear combination of the preceding vectors. Okay, so I'm going to give a warning after this. So my warning is just like the warning before. This does not mean that every vector in a linearly dependent set can be written as a linear combination of the others, right? It just means that at least one of these is a linear combination of the others. Okay, so the same warning applies as before. Okay, so the idea here, like what is the thing? You're looking at this and you're saying, I've seen all of this before. What's the difference? The difference is I could be talking about vectors here that are not vectors in the usual sense. They're not immediately given to you as n tuples of, you know, some vector with n entries, right? Like in Rn. And so for that reason, it might not be apparent immediately how to express this as an equation in the proper way. You might not be able to write it out as like a system of n linear equations in an obvious way. And so dealing with this more generally, this allows us to define linear independence more generally, just talking about vectors in abstract vector space. Now, it's going to turn out that those problems I mentioned aren't really problems. You could make it work in a finite dimensional vector space anyway. Again, I used the word dimension. I said I wasn't going to do that. So anyway, okay. So the main key thing here is this is going to allow us to define the notion of a basis, which intuitively is like a most efficient spanning set for some subspace. Okay, and so here is a definition. This is a very, very important definition. So maybe I should put a star here. So this is the definition of a basis. This is extremely important. So let H. You've already seen this. Regardless of your background in math, you've seen this because this is an extremely important thing in math in general. So let H be a subspace of a vector space V. A set of vectors say B1, B2, all the way up to, say, BP, is called a basis for H if, let's call this set script B. Okay, so we'll call that set of vectors script B. So needs to satisfy two properties. One, B is a linearly independent set. And two, the subspace spanned by B coincides with H. So H is equal to the span of the vectors that make up B. Okay. So, quick question. What is this? So the answer is intuitively this encapsulates the idea of a minimal spanning set, or most efficient spanning set for a subspace. What do I mean by that? Well, I mean that if you have a basis for a subspace, then compared to any other spanning set for that subspace, the basis is the most efficient. Okay, it is the minimal spanning set. And in a sense that we're going to make very precise here in a second. So there's a theorem I'm going to state that's going to 100% encode that data. But the main thing is that this just allows us to talk about a minimal spanning set or most efficient spanning set. So if I have a basis for a space, that is a really, really good thing to have. Because what it means is that if I had if I took any of those vectors in my basis and I threw them out, then I would no longer have a spanning set. And if I added any more vectors, well, it would be redundant. I already get the job done with less. That's the intuitive idea. So the reason why this is so nice won't be apparent until later, until we've done some things that apply this. But you've already seen examples of bases already. So so what are some examples here? Let A be an invertible matrix. So if A is an invertible matrix, it's an n by n matrix. So I have an invertible matrix, it's n by n. So let's say we have columns here, A sub 1 through A sub n. As an invertible matrix, what's one of the things that I get? If it's going to be invertible, the columns form a basis, right? So then the columns of A form a basis for Rn. How do I get that? Well, they span Rn and they're linearly independent. Okay. All right. So there's one example. Let's do more. Okay, so consider let E sub 1 through E sub n be the columns in the n by n identity matrix. Okay, then what are these things? So E sub 1 is the vector 1, 0, 0, 0, 0. E sub 2 is the vector 0, 1, 0, 0, and so on. Keep on going all the way out to E sub n, which is zeros all the way to the last entry. Okay. Then the set containing these vectors makes up what is called the standard basis of Rn. Those are called the standard basis vectors. Yes, so in R3, these are the ijk's, right? And what did you use when you were doing Calc 3 and you were dealing with the ij's and k's? What was the purpose of writing out those ij's and k's? So those are the standard basis vectors E1, E2, E3. That's ijk. The entire purpose of that notation was the fact that any vector in R3 could be written as a linear combination of ij and k, right? So even like built into that ijk notation is this statement that ij and k are a basis for R3. So that's what I meant when I said that you've seen this before. So you've seen this before in some way. Okay. But then how do I check whether or not something is a basis? Abstractly, to check whether or not something is a basis, well, I got to check these two things. I got to check whether it's linearly independent, and I got to check that it actually spans the thing that I'm claiming it's a basis for, right? So there's some info here. When I say that something is a basis, that's not just in a vacuum. It's claimed to be a basis for some subspace H. Now, you could go in the opposite direction. If I give you a list of vectors, then you could just define H to be the span of those vectors and then say, are they a basis for the subspace they span? That's fine. And I mean, that is, in fact, in a lot of cases, how you're going to talk about them. So in that sense, you can talk about them being a basis for some space always, right? So even in a vacuum, you can. But if I say, that a list of vectors, if I want to know whether or not a list of vectors is a basis for some given subspace, I have to check that they're linearly independent, and I have to check that they actually span the subspace in question. Okay, those are the two things that have to be checked. Okay, and so how might I do that practically? All right, so let's say say v1 be the vector 3, 0, minus 6. Let v2 be the vector minus 4, 1, 7. And let v3 be the vector minus 2, 1, 5. Okay. So is the set v1, v2, v3 a basis for R3? Okay. So what do I do? So there's a lot of things I could say here. There's a lot of equivalent methods I could use for answering this question. Okay, so what maybe is the easiest way? The first example, there's a reason why my first example of a basis involved considering the columns of an invertible matrix. Right? Chapter 3 gave us one means of computing whether or not a matrix was invertible. That's something we could use. Or we could just form the matrix in question and ask ourselves some some relevant questions about it. And so, how do I check? So to check, I form A, which takes those vectors as its columns. Okay. And what do I want to do? I want to know whether or not this is invertible, right? So is A invertible? Okay. Now it turns out that this A is. There's a number of different ways that you could check. So it turns out, yes, it is invertible. Since A is invertible, they form a basis, Y. Thus, the set is linearly independent, and the span of the three vectors is equal to R3. This is easiest to check by checking whether or not this matrix is invertible. But how did we check? I just said it turns out. So I want you to check. How do you check? You can compute the determinant of A. It's a 3 by 3. There's not that many zeros there, so might be a little work. So you can compute the determinant of A. See if it is 0 or not. That's one thing you could do. What's something else you could do? You can perform row operations on it to see how many pivot positions it has. So in fact, 2 row operations, I believe 2 row replacements show that it has 3 pivot positions. So you could also row reduce, look at pivots. Okay, that's another thing you could do here. So either of these works perfectly fine. This gives you one way or this gives you a way of seeing how you might efficiently check whether or not something is a basis. Okay, so more. Here is the thing that actually codifies why this intuitive thing I said about bases is true. So here's the theorem. This has a name. It's called the spanning set theorem. Okay, so let S be the set of vectors v1 to v. I shouldn't use n there. Use p. Here be vectors in v, and let h be the span of those vectors in S. Okay. All right. Then 2 things. If one of the vectors in S, say v sub k, is a linear combination of the others, so of the remaining vectors in S, then the set formed from S by removing v sub k still spans H. So tossing out vectors that are linear combinations of the other vectors in some spanning set doesn't actually affect the span of those vectors. So if you toss out a vector that's a linear combination of some, basically it was a redundant vector that was giving you no new info in the first place. And secondly, if H is not the 0 subspace, some subset of S is a basis for H. So this is what ties together that intuitive stuff I was mentioning earlier, that a basis is the most efficient spanning set. So what this is telling you actually is a process that is going to terminate eventually, because there's a finite list of vectors here. Okay, so you have a process that's going to terminate eventually, where you look at this. If there is no vector here that is a linear combination of the other vectors, well, then that's a linearly independent set, and you have a basis, right? If there is some vector, say vk, that's a linear combination of the remaining vectors, you can toss it out and you still get a spanning set. Repeat that process. Is there another vector that's a linear combination of the remaining vectors? If not, you have a basis for H. If there is, toss it out, you still get a set of vectors that span H. And so you can continue this process until you get a basis for H. Necessarily, that basis is going to be a subset of the original list of vectors. Okay, so that's how this works. So this is what ties together our notion of a basis being the most efficient spanning set. Okay, so we'll be doing a lot here. We're going to be computing bases for the null space and the column space next, and then moving on. So we'll be moving on, talking about coordinates and change of coordinates, change of bases stuff that's coming. And finally, we'll be able to bring up the notion of dimension. That's going to be the main thing that we get out of this talk of bases. Okay, so a couple things. One, your exam is next Friday. And when I say it's next Friday, I will post it next Friday, and then you'll have next weekend to do it. Also, your homework that was due today, I extended it. It's due on Monday instead, because I'm going to have office hours Monday afternoon, right after class, where you can ask any lingering questions you have about the homework or about the material up to that point. Your exam is going to cover through. We'll say it's going to cover through 4.4. I think that makes sense. Does that make sense? Yeah. Well, I'll post that anyway. I'll post what your exam covers through. Actually, it may go through 4.5. I think that makes better sense. Anyway, so and 4.4 will be, 4.5 is dimension of vector space. 4.4 is coordinate systems. So it's going to cover at least through dimension, I think. So 4.5 is dimension of a vector space. Okay. Anyway, so homeworks will be graded. So your first homework should be finished graded sometime soon. I noticed that there were, like, at least some of them had been graded last I checked. So anyway, so yeah, I will see you all on Monday.